Okay, pause and copy. Pause and copy. We are on to my favorite chapter. Not always the student's favorite chapter, but certainly my favorite chapter. Okay, let's go through this. Okay, we're gonna approach this by thinking about blueprints and houses. Okay, so if you drive through a suburb, you will see many houses that look pretty much the same. Maybe Tommy Johnson has a pool in the backyard, and Jimmy Jacobs doesn't have a pool in the backyard. Maybe Tammy um, Blackowitz has a Christmas decorations, and Joey Jojo doesn't. There's differences, but these houses have a lot in common. They all look the same, right? They all have the same, well, you'd say they all have the same blueprint, right? They all have the same basic structure. So here is our blueprint, which we'll be using. So there are objects, and there are two operations, addition and multiplication by scalars, or just say scalar multiplication. Okay, this is a lot to digest, so I think we should jump into some actual houses. Okay, so these are more familiar, especially R2 here. Okay, I want you to think about R2 in connection with these 10 axioms up here. If I take two vectors in R2 and add them together, I don't magically escape R2, do I? No, I'm still in R2. Okay, so R2 passes this condition. There's some arithmetic things here that I think you'll agree that in R2 it's A-okay. There is a zero vector. All right. If I have a vector, say 2, 3, then I also have the vector -2, -3, right? So you always have a negative of any vector. If I multiply by a scalar, I don't escape R2. And the remaining things are kind of arithmetic, explaining the connection between scalar multiplication and the addition operation. Okay, so I think for 1, 2, and 3 down here, you can convince yourself that these are all vector spaces. Now, we've been using the word vector since chapter 1, and we're going to use it a little bit differently now. Okay, what is a vector? A vector is something that is in a vector space. So if I look at number 2 here, a polynomial like, let's see, 3 minus t squared. We're going to be thinking of that is a vector in P2. Okay, so that's a bit strange. This chapter is going to be a bit strange. I'm going to ask you to keep an open mind here. Okay, this is a sometimes abstract topic, and I think most people prefer to stay in the land of actual houses. But we're going to be asking you to spend some time in the world of a blueprint. For example, let's do some blueprint questions. Okay. Copy this one down. Now, here I am strictly in the land of my blueprint for a vector space. Okay, you need to remember that. You are not thinking about an actual house here. You are thinking about, as you try to demonstrate this perhaps seemingly obvious statement, you have to remember that the only tools you have are these here, okay? If you want to prove this, you can't say, 0 times a vector is 0. No, you can't. That's not, that's not, that statement is not on this list here. So I need to prove that 0 times any vector is going to give me the 0 vector. And I have to do it using axioms 1 through 10. Okay, let's try. Let's see what I do. So I'm going to use some clever tricks here. I'm going to start by doing a not so obvious calculation. I'm going to start with u plus 0 vector. Okay, I should underline that this 0 here and this 0 here, those are quite different, right? Here we're referring to the 0 vector as described in the vector space definition. And here we're talking about the real number 0. Okay, back to my calculation. U plus 0. Why am I starting here? Well, it is it's a question of technique. I'm trying to make my demonstration happen, and we're going to see that this works. What is u plus 0? Well, that is equal to just u. Well, I need to say why. For what reason? Well, that is axiom number 4. Put a little 4 here to indicate I used axiom 4. Now, what is u? Well, u is 1. The real number 1 times u. And what axiom did I use there? I used axiom number 10. Next, what is 1 times u? Well, I can expand. This is 1. All I'm saying here is 1 is equal to 1 plus 0, real numbers. Okay, so I don't have to quote an axiom there. That is merely, I don't have to say anything there. Okay, all I'm saying here is that these real numbers, 1 and 0, add up to the number 1. Next. Okay, here I'll use an axiom. I can do a distribution, which is guaranteed by axiom 8. Finally, 1 times u is u. That is an axiom plus 0u. What does that get me? Oops, got to quote my axiom here, 10. So what does this calculation get me? Well, it tells me that u plus 0 is equal to u plus 0u. So I want to Well, I want to prove this, right? So I want to just cancel what I want to do, but I can't, is just go bloop, bloop. But just going bloop, bloop is not one of the axioms 1 through 10. No bloop, bloop. So I want to cancel the use. So what I'm going to do is I'm going to add something to both sides. If you have an equation and you add the same thing to both sides, then the equation still holds. Okay, so this is a piece of logic that I hope you agree with. Okay, this is getting a bit tedious now, but let's just go through it. Okay, now what do I need to do? I need to rearrange some things. What do I want? What I want to do is go bloop, bloop, right? So I want my U's to cancel. But I need this guy and this guy to be beside each other. So I have to go through this carefully. So I'm going to go and change the order here. Likewise on the other side. Oops. 0 U plus U plus negative U. Okay, which axiom is that? I have forgotten. I did the change of order of this one. Axiom 2. And now I want to go 0 vector plus. I want to change my bracketing here. Oh boy, this is really getting tedious. Plus negative U. So what did I do there? I changed my bracketing. How so? How can I do that? Well, let's have a gander. Which one of those? Oh, that's number 3 up here. Changing the bracketing. So let's quote that. 3. And this becomes a 0 vector. This becomes a 0 vector. So what did I do there? I used the cancellation property. Which one is that? It was this one here, number 5. Holy. Even I'm getting tired of this. Now what? The property of the 0 vector. What does that do? It tells me that 0 vector plus anything gives me, so 0 vector plus anything gives me just that thing. Which one is this? 4. Holy moly. And there we have it. I have demonstrated what I want to demonstrate. Okay, to indicate to your reader that you are done, you can put a little rectangle here or a square. A little square sometimes does it. If you don't like the square, you can write QED. I think that's Latin for, I have demonstrated what I wanted to demonstrate.